Hello everyone, welcome to the new webinar organized by VALVecampus. I'm Virginia and I am one of VALVecampus organizers. VALVecampus is an association of manufacturers, industrial valves and components for oil and gas and power industries. It's a good place to learn, to be informed, to develop a business, to build a network, to be part of the community. These are the reasons for become a member. Today's topic is on additive manufacturing. The last minutes of presentation will be the question and answer part. Please write your question in the chat box. It's now my pleasure to present Roger Lerum, Head of Equinor Strategy, and I hope you enjoy our presentation.
Thank you. I'll just share my presentation. Okay, thank you very much for having this opportunity to speak to you all. My name is Ray Delarum. I work for Equinor. I am the head of the AM strategy and implementation. That means additive manufacturing. I've been 22 years in Equinor and I've had various engineering and management positions within operations, maintenance and modification. And for the last 3 years, I've been working with digitalization and additive manufacturing. A few words about Equinor. We are the main oil company in the Norwegian continental shelf. We produce 2 million barrels per day. We operate more than 40 assets on the Norwegian continental shelf, so we have the majority of the activity on the Norwegian shelf. And we have also started operating in other countries. We are present in 30 different countries, and the Peregrino field in Brazil is our largest international operatorship. But we also now define ourselves as an energy company, so we've also started working with other kind of new energy solutions. So our goals now are to produce between 4 and 6 gigawatts of electricity from wind turbines. We have already cleaned and deposited 23 million tons of CO2. So the CO2 issue is very important for us. And we have a very ambitious plan for reducing the CO2 emissions from our activities. We now call ourselves the digital energy company, and we have 3 main issues that we try to live by. First, we should always be safe. That's our primary target, of course. We want to produce high value and low carbon. So that means low carbon is one of our main concerns when we produce energy. We've started our digital journey a few years ago, and quite early we defined a digital roadmap that you see now on this slide. We are divided into 6 different program areas where we are working with different digital topics, and the additive manufacturing initiative is part of the data-driven operations that you see as number 5 here. But in the center, we have a data platform that is more or less the heart of our digital strategy. In addition, we are working with many different technologies, and to the right, you see that additive manufacturing is one of our technologies that we believe is going to make life easier for us, reduce cost, and also reduce the environmental footprint. So I will first show you how our additive manufacturing strategy is. I will show you a little bit about how we believe the development for the suppliers and for the operators, how we can work together in a better way in the future. And I will also show you how additive manufacturing can reduce the environmental footprint. But first of all, the additive manufacturing strategy. We believe that additive manufacturing is an important tool, but only one of several digital tools that will make us improve in the future. But one of the main areas we are looking into is how we can go from a situation where we do a lot of things just in case. For instance, as you see on the picture, large physical inventories, and most of those components that we have in our physical inventories will never be used. We just buy them, put them there, just in case we need them. If we can move to a just-in-time philosophy, we can save a lot of money, but also a lot of environmental footprint, because we can reduce how many components we actually produce. That means we have to transform the way we work into a digital way of working. So we want to move from large physical inventory, and we have approximately 3 billion euros worth in our physical inventories. It's a lot of money just lying there, and we don't know whether we're going to use them. So by moving to the digital inventory, which is also a very important part of the additive manufacturing transformation, then we can fill it up with 3D models, connect it with a digital supply network, and then produce the parts we need just in time. In addition, we see that the issue around obsolete parts is very important for us. The oldest platforms that we have in the Norwegian in the North Sea, they are 40 years old, and sometimes it's very difficult to get spare parts for the systems that we have on board. But using 3D scanning, reverse engineering, or new engineering, and then 3D printing, we can get those parts that we need. That means we can extend lifetime of platforms, of systems, and of components. The other area is maintenance cost, which is very high on the Norwegian continental shelf. And in many cases, when metal parts are corroded or worn, we discard them and replace them with new. Now we can repair those metal parts with 3D printing. And it's actually a very important way of reducing the cost on our platforms the way we see it now. The next thing that I know that Valeria will say more about is that we can improve the performance of our components by using the new opportunities within additive manufacturing. So by improving performance, we can reduce the maintenance cost because we can make the components last longer, or we can even increase our production because we can remove pain points, bottlenecks, areas where we have pressure drops and so on. So I believe strongly that in the future we will see a rapid increase in our performance because we can produce much better components. And I think that is really a very important job that you have in the future, to develop much better components using the new tools that we have within additive manufacturing. And then the last thing is long lead time. And in many cases, time is money. And if we can reduce the lead time, that is very important for us. So if we have the 3D model and we have 3D printing capacity, and we have the competence, and we can have routines for certifying those metal parts, we can reduce the lead time from months to weeks. And that is a very important transition for us. So actually we see that the additive manufacturing transformation can help us improve safety, operations, maintenance, modifications, reduce inventory, and reduce our carbon footprint. So what you see is it's a big picture. It's not just a matter of printing parts, it's a matter of transforming the way we work. So our vision is, we have set a step ladder on how we're going to get there. But to lead you all the way to 2028, we believe this will take some time to do this transformation. But in the future, we will have a digital inventory and a digital supply network that is fully integrated in our systems. The spare parts we need will be available just in time, and the physical inventory that I showed you, 3 billion worth of euros, can now be reduced to the full potential. And we believe that we will have a distributed 3D print capacity available, driven by the suppliers. So Equinor is not going to build 3D printing capacity on our own. We still want you, the suppliers, to do that. So then to the next picture. The digital inventory will be the heart of this ecosystem, and we have divided this into 4 main roles. Equinor comes in as the end user, but there you will also find, of course, Shell and ConocoPhillips and all the other oil companies. But if you have the right quality, you can produce parts for anyone, not just the oil and gas. You can produce for armed forces, for the shipping industry, for medical use. So additive manufacturing can be used for any industry available. Then the next role is the IP owners, and that is really the OEMs that we see today. But in the future, we need you to sell us digital parts. And we want to be able to buy digital parts from anywhere in the world, but preferably in Europe, of course, because that's closer to where we have our main office. But then we want to produce the part in these just-in-time factories. That's the JIT, just-in-time factories, and they should be anywhere, spread out wherever we have our activities. So that means if we need a part on a platform in the northernmost, in the Barents Sea, we would like the production of the parts to be in northern Norway. If we need a part in Denmark, we would like the factory to be in Denmark, and so on. And I know that the other oil companies, they have the same way of thinking as well, that if they need something at a plant in Italy, it would be much better to produce the part in Italy. And then in this ecosystem, we want also the verifiers like Lloyds or DNV-GL to verify and certify the parts whenever we need a certification stamp. And we want all these parties to be connected in a living and thriving ecosystem. And whenever we as the end user post a need, everyone can see it. So everyone can start working on this order or the purchase order, and we can reduce administration and reduce the time needed to produce those parts. So we want to move from a traditional linear supply chain where we know we have a lot of delays, we have a lot of controls, we have a lot of costs, and we have a lot of extra administration between all the different chains in the supply chain. So shifting then to the digital inventory, where we have a digital supply network, it would be much more efficient, and everyone can act on the original need that the operator has. So we have already started the project with a digital inventory together with Siemens and a company called FieldMade. And within a year and a half from now, the digital inventory will be implemented and we will start working according to the digital supply network model that you see on this figure. So it will be a very large change. It will be a big leap for us, but I strongly believe that this will make both you as the supplier and us as the end user much, much stronger when we can do this transformation together, and we can hopefully get better margins also in the future. So I will soon wrap up, just illustrating how additive manufacturing can reduce the environmental footprint. First of all, if you see the picture in the middle, component number 3 is a traditional produced part. And number 1 is the metal block you need to start with to produce part number 3. And number 2 is the amount of waste that you get when you machine this part. Number 4 is a exactly same component with the same function, but optimized for additive manufacturing. And number 5 is the amount of metal powder that you need to produce this part. And number 6 is the amount of scrap metal you get from the production. So this is just an illustration of how efficient additive manufacturing is compared to the traditional manufacturing methods. The other area, if you see the diagram to the right, if we can extend lifetime of components, extend lifetime of systems, and continue the maintenance circle here, that's the cheapest and gives us the lowest environmental footprint. If you reuse, remanufacture, or recycle, you increase the footprint. We've also calculated that recycling, you can get back half of the energy, but that means 50% of the energy is lost by recycling. So actually extending lifetime is the most environmentally friendly. So using the model that you've seen, we can reduce transport, which of course reduces the CO2 emissions. We can reduce the waste, that's what you've seen on the picture. We can reduce the use of raw materials and thereby reduce the CO2 emissions. So this is actually adding up to quite a lot of CO2 if you start looking at this. So Hydro and Valeria and Equinor, and we had a student in Norway who started calculating this. And on the illustration, you see a manifold produced with conventional manufacturing, then exactly the same using additive manufacturing, and then the last one optimized for additive manufacturing. And the CO2 emissions for the conventionally produced manifold is 67 kilograms of CO2 equivalents. But then just moving to additive manufacturing, producing exactly the same, reduces the emissions with 50%. And then optimizing the topology of the component, you can reduce the CO2 emissions down to just 13 kilograms. So it's really significant reduction of CO2 emissions. And the last example is in the case where one of our suppliers said that because the cooling fan you see on the picture on the top was broken, we had to replace the whole electromotor with a weight of 1.5 tons. So we went to a supplier who produced a new fan using additive manufacturing, and the CO2 emissions for 3D printing this fan is 3.8 kilograms. But on the right, you see replacing the whole electromotor, there is a CO2 emission of 4.5 tons of CO2. So for us as the end user, it's a huge picture, and we can see a large reduction of CO2 emissions if we use additive manufacturing to reduce our consumption of raw materials. So this is significant and very important findings that we will pursue in the future and make sure that in the future we can reduce cost and reduce environmental footprint. So this is just a few pictures of different components that we have produced together with suppliers. And in the future, we'll see a rapid increase in number of components that will be produced using additive manufacturing in the future. So by this, I will send the word to David. And when all four are finished, we can have a question and answer session in the last 30 minutes. Thank you.
Thank you very much, Frida. I'm going to try and share my screen now, so please let me know if this appears.
I see it now, David.
Perfect. Thank you very much, and good afternoon, everybody. So my name is David Hardacre. I work for Lloyd's Register, and I'm based in the UK. Just a little bit about me. My background started in control and instrumentation on nuclear submarines before moving into aerospace, which is where I got my first experience of additive manufacturing, designing a gas sample rake to be manufactured using powder bed fusion. And then I joined Lloyd's Register in 2011, working on pressure equipment, so including design appraisal of valves and various other types of pressure equipment. And probably for the last 7 years, I've been working on additive manufacturing for Lloyd's Register and contributing to a number of standards committees, such as the ISO and ASTM committees on additive manufacturing, API 20S for oil and gas, which Carlo will be speaking about a little bit later, ASME for the boiler pressure vessel code, and Technical Committee 54 for EN 13445 for pressure equipment in Europe. So we don't have very long, so the topics I'd like to cover this afternoon are different approaches to certification between industries, quality control and certification, expectations on the manufacturer, and engaging with certification authorities, all from the point of view of additive manufacturing, of course. So, as Frida said, additive manufacturing gives the facility the opportunity to serve not just one industry, but multiple industries, be it oil and gas or aerospace, medical, automotive, etc. And it's important to understand the different approaches between those different industries. But coming back to the root of the question of why do we certify in the first place? Well, it's primarily for safety. It's the safety of the operators of the equipment that we make, consumers of that equipment, and even the members of the public who might be living near a facility or going to school or going to an office or working in a shop close to a facility where an additively manufactured component is in use, and failure of that component could result in a hazardous incident. So that's why we certify, to give assurance that the part is safe to use and fit for purpose. The other reason for certification is product assurance. It's to benchmark one AM facility and demonstrate where they are compared to others, you know, what their capabilities are, or even to benchmark a particular product or material in terms of what is available in other places on the market. When it comes to different industries and different certification approaches, if an additive manufacturing or an AM service bureau is used to serving aerospace and medical industries, then they may be used to working in a certain way. So for those industries, the tier one, as I will call them, will write a specification which gets audited by the regulator. So the Civil Aviation Authority, for example, in aerospace, or the FDA for medical. That specification is then flowed through the supply chain, and different members of that supply chain will have to meet or satisfy the requirements that are applicable to them. This gives the additive manufacturing facility quite clear guidance, and they can get on and work and produce the parts and test and produce test reports and provide those up the supply chain. What you need to be wary of, though, is when working for other industries, such as oil and gas or marine, for example, then third-party certification is a legal requirement. So regardless of who the inspection authority is, there will be certain witness points that are required. So as an AM Service Bureau, you would be required to agree in advance those witness points, such that you didn't progress beyond a certain point without having the inspector come on site and either review a document or witness a test, whatever the witness point might be. What you don't want to do is go into production, make something, test it, miss that witness point, send off the report, only to find that you have to make it again. So an AM Service Bureau that is used to working for aerospace and medical clients that now wants to work for oil and gas or marine clients does need to be aware of those differences and the expectations from the inspection authority. So here's a little bit of fun for a Tuesday. This is a Rube Goldberg machine. You've probably seen different versions of these before. The objective of this one is to extinguish the candle. What you can see is that there is a process in place. There are a number of steps that the ball has to go through in order for the cup to tip correctly and extinguish that candle. Like any process, we can break it down into different stages, and the probability of success of the overall process is the probability of each step succeeding to the power of the number of steps. So in this case, let's say there are 10 steps. Each step has a 90% chance of success, which gives the overall system a 35% chance of success. As we can see there, various things can go wrong at each of those stages. So what about additive manufacturing? What does this mean for AM? Well, there are more opportunities for failure. So if we start at the beginning of the process, at the design stage, there are variabilities in terms of the build orientation, different material properties depending upon build orientation and location. Errors can occur during the translation or fixing of a CAD geometry. So the native CAD geometry needs to be translated to an STL file, which is then translated to a slice file. And in between those two events, certainly for powder bed fusion, offsets might be applied for a machining allowance, or support structures might be added. Various opportunities for error and variability. Also, if you're designing for AM, What about the design factors? Do I need to apply a different design factor? So a casting factor, for example, would reduce the stress allowable within your design calculations. Are existing fatigue curves relevant and applicable for additively manufactured parts? When we come to the feedstock, so again, thinking about a powder-based AM process, the powder itself carries a whole host of risks. So there's the possibility of contamination during the powder production process, which is typically gas atomization, but that's not the only powder production process. Storage and handling carries a risk of cross-contamination between different powders or pickup of oxygen or moisture, depending upon its if it's ever opened to the atmosphere. Recyclability of powders. So the great example that Breda just demonstrated with the small amount of waste for that particular component, that's only true if you can recycle the powder that's not fused, that was deposited within your build chamber. So recycling that powder also carries certain risks and variabilities. The AM machine itself, obviously consistency between machines, different build parameters, installing that machine and then commissioning it, performing a site acceptance test to prove that it is operating within expected parameters. The build process itself, so once you've qualified your equipment, so you've gone through an installation qualification, and then you've done an operational qualification, which will be producing some material specimens and proving a consistent output. Then the build, you get onto building the part itself, and then again there's more opportunities for risk and variability. So the recoater that passes over, that spreads the powder, you can get short feeding if you haven't got enough powder on there, or the recoater itself could carry some contaminants, so you need pre-build checklists to make sure that that is clean, free from debris, free from any nicks or cuts or grooves on the recoater blade. And then after the part is made, obviously you've got the post-processing. So it typically during a additively manufacturing process, there is significant buildup of residual stresses due to the rapid heating and cooling. So you want to take care of that. You want to perform a stress relief. So there might be different heat treatments. You might perform a hot isostatic pressing or a HIP cycle. You might perform a solution anneal. Is it the same heat treatment that you would apply for an additively manufactured part compared to a conventionally produced part? And what about the inspection, the non-destructive examination? Are typical inspection techniques such as ultrasonic examination or radiographic examination, are they going to be suitable for picking up the different defects that can occur with an additive manufacturing process? So for example, trapped powder isn't a defect that you would typically look for in a conventionally produced material. So is radiography going to be capable of picking up that sort of defect? So there are various hazards, various risks that can occur through the process. And the takeaway from this is that if you were to map out this process, let's say there were 131 opportunities for this to fail. So just like the Rube Goldberg machine that we saw on the previous video, instead of 10 steps, we've got 131. If we had a 90% confidence that each step was going to succeed, then that would literally give us a 1 in a million chance of the overall process succeeding. Now, the good news is that 90% is actually pretty low for a probability for each step. So if we were to ramp that up to 99% for every one of those 131 steps, then we get a much better result, 27% success rate, but that means the process is still failing 3 times as often as it's succeeding. So we really need to ramp this probability of success up. And by the way, 131 steps is probably quite a low estimate. There are Ishikawa diagrams for different AM processes that typically have more than 150 steps or opportunities for error. So the conclusion here is we need to identify these opportunities for failure. We need to mitigate them through control of the process, control of the system, or testing and inspection in order to give us a good overall confidence that the whole process is going to be successful. So the expectations on the manufacturer, in order to certify an additively manufactured part, a prerequisite of that will be to certify the material that forms it. In order to certify the material that forms it, we need to qualify the facility, the additive manufacturing facility, and we can typically split that up into three foundation stones, looking at the design, the feedstock, powder or wire typically for metal processes, and the build plan. And if we look at the documentation that's produced to control these processes, we can split that up too. We can look at a manufacturing plan, which covers what is being manufactured, so perhaps a valve, and that will be everything that goes in here is specific to the part, regardless of the facility where it's being made. And through the facility audit, we will be reviewing facility procedures, which is about how that part is, or how any part is being made. So this is specific to the facility, regardless of what you're making. And over the process of a project, various documents will be produced, which go into one or other of these documentation packs. So sampling procedure you would expect to be the same every time, calibration certificates there for the equipment that you're using, but the CAD model and build layouts, which we would review, form part of the manufacturing plan. And there are various other aspects as well, like a job control card that specify each step in the process and who has performed what at what time. And one of the essential variables in this process that we often don't talk about is the operator. It's the people operating the equipment or programming the equipment or performing that translation. So competency of operators is a main function as well. And at the end of this process, going through a typical project, the inspection authority would issue an inspection certificate, which covers the design, the appraisal of the design to make sure that it's fit for the application, all of the powder testing, all of the material testing after the build, any non-destructive examination, etc. And that would allow then the part to be certified for use. So throughout the stages of a project, we typically talk about 5 functional stages of design, materials, manufacture, post-process and inspection. And there are various aspects that we need to cover in each of those stages to demonstrate that these risks have been sufficiently mitigated. And many of them are mitigated during this facility audit, where we're looking at the manufacturer's processes and procedures and competency of operators, etc. Now, when we talk about a facility audit, once again, between industries, there are different approaches. So in aerospace, there's the NADCAP system, AC7110, ASTM F3303, which is specific to powder bed fusion. AWS D20.1 is an excellent specification. One advantage of this is that it covers more than just powder bed fusion. It covers direct energy deposition processes as well. And then AMS specs in aerospace, the API 20S specification for oil and gas, which Carlo is going to speak about. That's at draft at the moment, but one of the advantages there is not only will that cover powder bed fusion, direct energy deposition, but will be, I think, the first to include all three, binder jet as well, for metallic parts. And other specifications and guidance are available. But what is common between all of these systems is the sets of requirements. And so they all cover this basic set of requirements, looking at these aspects in order to mitigate those risks and find mitigations for those opportunities for error. So in summary, look at if you're an additive manufacturing service bureau, be knowledgeable of the different aspects to certification for different industries, know the requirements for the industry that you're serving. Quality control and certification, controls at every stage to maximize the probability of overall success, break down your process. Know the expectations on the manufacturer, what documentation you're going to have to produce at what times and where those witness points are, because when you engage with the certification authority, engage early, agree those witness points such that you don't progress too far without having the inspection authority there to sign it off. And in that way, you'll avoid rework, avoid cost and time deficiencies on your project. Okay, so that's all I have to say for this afternoon. So at that point, I'd like to hand over to Valeria from Hydro, who is going to present about what Hydro are doing. Thank you very much for your attention.
Thank you, David. So, hello everybody. I'm Valeria Tirelli, and I'm very happy to share the stage with such great experts from the oil and gas industry. And I'd like to tell you more about my personal experience and my company story. Hydraulics and 3D Printing is an Italian family-owned company with more or less 40 years of experience in the hydraulics business. A few years ago, we introduced additive manufacturing to create an innovative business for hydraulics parts. And then we learned about this technology, and I can say we are really enthusiastic about the potentiality of additive manufacturing, and we are now a kind of pioneer to promote the use of additive manufacturing in hydraulics in the oil and gas and other sectors. I'd like to tell you more about the fact that every day we listen and we read that additive manufacturing will grow more and more in the future. And I'd like to tell you if this technology, new technologies, has some benefit also in a sustainable development. I will show you the advantage of additive manufacturing in different stages. First of all, I will show you some case studies, some products produced with additive manufacturing, and in this case, we use less material, which means that we need less energy to produce the parts, and we have also less waste material, as already shown by Brede in his presentation. I will tell you also something about the benefit of using additive manufacturing to improve the process's performance, thanks to the fact that we can create smart and small components that can improve the chemical efficiency of different processes, like, for example, in gas treatment systems. And at the end, I will tell you about a new project of circular economy created by an Italian startup called Fenice, in which the aim is to recycle material from scrap material from the commissioning to create new smart parts with additive manufacturing. So let's start with some example of parts. I will show you the parts from my company experience, so from hydraulics. This is the traditional manufactured hydraulics manifold. This part was made in aluminum and the weight is 5 kilos. Thanks to additive manufacturing and the possibility that we have to redesign the parts, we have created an optimized hydraulic manifold with 75% weight reduction, and the final weight is only 1.3 kilo. This is a huge weight saving, and also less energy was used to produce this part. But I show you also which is the application. This hydraulic manifold is installed in a portable power unit used in offshore platforms. This means that the power unit with the hydraulic manifold that you can see with the red flag is transported from, the factory to the offshore platform in helicopters. This means that saving 4 kilos means saving cost and a lower payload. Another example of parts made with additive manufacturing is the new shapes that we can create. For sure you have listened about lattice structure. Is this incredible shape that we can have only with additive manufacturing, meaning adding material layer by layer and create these innovative shapes. The use of these shapes is well known in heat exchanger. This is an example of heat exchanger made with an internal structure called gyroid. I show you now the example, the comparison between the conventional heat exchanger shell and tube that everybody knows, around 11 kilo of weight, and the redesigned heat exchanger made with additive manufacturing that allowed us 85% weight reduction and a very, very small size. You can imagine that the better performance, the higher efficiency in a smaller parts can give us a lot of advantage. These are only few examples that I show you, but there are many other components that can be produced with additive manufacturing. You have already seen this during the birthday presentation. This is an hydraulic manifold, and from the university, the Norway University, there was a study showing that the reduction of weight, meaning in this case it was 60% weight reduction, means also a very big saving in terms of CO2 emission, around 80% CO2 emission reduction. This is really impressive, what we can achieve with additive manufacturing and use this technology to produce parts. Speaking about CO2 emission, I'd like to show you other example in the use of gas treatment. This is the typical system where the dirty gas enter in the process, and thanks to a nozzle or different component, the gas is treated, and at the end we have a clean emission. To improve the efficiency of the system, we can create a 3D printed nozzle, like this in this example, in which the performance is improved thanks to the fact that we have internal shape with spatial channel or spatial holes that are feasible only with additive manufacturing. Other examples are this kind of compact tool that have internal round channel that again are possible only with a production layer by layer, adding material only where it is needed. And now, speaking about a circular economy project, this is very new project powered by an Italian startup called Fenice. The project aims to create an ecosystem using the material from decommissioning to create a new generation of 3D printed parts. The idea is to recycle the scrap material and create a green material, a new raw material for new parts. And this part can be, of course, produced with 3D printing or additive manufacturing, but also we can create a digital file ready for 3D printing on demand. This is exactly in the same philosophy, same approach that we have already seen during the birthday presentation for the digitalization plans. I'd like to tell you more about the decommissioning of oil and gas plants from the North Sea. You will see here some data from a research and analysis. You see how many amounts of tons there will be decommissioned and discharged in the next 4 years. It's about 800,000 tons, including topside and subsea plants. This is a very huge amount of material, mainly metal material. And this process will create a value of about $17 billion. A part of this value is linked to the material disposal. So the idea is to use a part of this material, especially the higher value material, like for example, stainless steel or Inconel, to create a new raw material for new parts. So avoid to waste only the material, but create something new and recycle the parts. This is the ecosystem. So the idea of Fenice is to create an ecosystem in which many different actors, many companies will work all together for the same aim. So give a new life to the old parts. The idea is to start from the oil and gas plants. This is the idea, but of course all the other plants like chemical or industrial plants can be involved in this project. Then collect the scrap material that normally is discharged during this decommissioning process. use this as raw material for the powder production, and create a new raw material for additive manufacturing with the correct particle size distribution or the chemical distribution that is needed for additive manufacturing technologies. We are now speaking about all different technologies, from laser power bed fusion to metal deposition or binder jets. But let's go further in the example. The idea is to use this green powder and, taking into account the properties of this material, design new parts or redesign the traditional and conventional parts to take the benefit of additive manufacturing, meaning using less material to create it and use less energy. Then the process, so the metal 3D printing. In this example, you see the laser power bed fusion printer. And then all the post-processing will be done to achieve the final 3D printed parts. In this example, you have some valve components, and the idea is that these parts made with green material will come back in another plant, or like replace the old parts. And in this project, you see that the old parts, the scrap material, is able to create new parts with a new life. This is a circular economy project. This is just an example of a different approach for the future. That means that we can start to think differently in everyday process, everyday business that we do. Because I believe that we have to think at new businesses with a sustainable mindset. And we have to use all the available technologies, like additive manufacturing, for a better and a green future for our new generation. I think this is what we have to do. This is our mission, to guarantee a green future to our next generation. So thank you very much for your attention. You can see here my contact. And I'm very happy now to give the stage to Carlo De Bernardi from ConocoPhillips.
Good morning, good afternoon, everybody. My name is Carlo De Bernardi, and I am the additive manufacturing lead and the valve subject matter expert for ConocoPhillips. I'm based out of Houston, Texas. And today, I do not have a presentation because I'm not as good as my colleagues. But I will try to walk you through API 20S and trying to connect some of the dots that have been presented by the other presenters. So let's talk about API 20S. API 20S, the scope of API 20S is the qualification of metallic components manufactured by additive manufacturing. As David was pointing out, this document is going to cover three main processes that are powder bed fusion, direct energy deposition, and binder jet. So this will be the first of a kind encompassing or covering all the three processes. The reason why we are covering all the three processes is because they have their own place and we have our own needs that are covering that needs the three technologies. Why we started this API 20S journey? So as an oil and gas industry, we recognize that additive manufacturing has a lot of potential. However, there are risks. So we cannot discount the risks associated with the misuse of this technology. And because our first step as oil and gas is always to identify risks and mitigate or manage risks, we agreed between operators and OEMs that something needed to be done. So last year we started this task group, and today we have more than 100 members. We are meeting very often, virtually of course these days, so almost every week. These members are representing all the steps of the supply chain. So we have OEMs, we have end users, we have machine manufacturers, powder manufacturers, and universities and institutions. By doing that, we are gaining a lot of experience from people not only from the oil and gas, but also from aerospace and other type of applications that are contributing to the development of the document. So let's try to understand where API 20S is fitting within the API world. So most of the OEMs that are working in the oil and gas are familiar with API. API is one of the most utilized set of standards across the globe when it comes to oil and gas. And these standards are covering product specifications, material specifications, and supply chain specifications. API 20S is part or will be part of the API 20 series. The API 20 series is a supply chain spec. Why do we have a supply chain spec? We have a supply chain spec because these supply chain specs are, with time, included into the product specifications. So you can take as an example API 20A, B, C, E, and F, that they are covering castings, forgings, boltings, that now they are called out in several product specifications like API 6A, API 6D, so on and so forth. So eventually API 20S will allow two things. Will allow industry recognition of additive manufacturing, will allow the industry to define the safety operational envelope of use of additive manufacturing, and it will allow additive manufacturing to be utilized for the production of oil and gas equipment. So as of today, for example, if you take API 6A, it doesn't recognize additive manufacturing as a viable technology. With API 20S, eventually that step will be accomplished. There are other initiatives that are going on in the industry when it comes to industry acceptance of additive manufacturing, but I'm not going to cover them today because there are several joint industry projects that are happening or will be happening in the near future, and I cannot disclose them yet. But this API effort is a major one, and it will represent a step change for additive manufacturing in the oil and gas. Now, as I said, there are risks. So let's try to connect all the dots of the previous presentations. The overall goal that has been presented by Brede and then by David and Valeria is very, how can I say, aligned with what the industry needs and wants. However, there are many, many steps that we need to accomplish in order to get there. Additive manufacturing is a new tool in the toolbox. That doesn't mean that is the solution for every problem. As every tool, it has to be sustainable to be used. And this sustainability comes with a certain type of performance and a certain type of economy behind it. So the digital inventory, it is possible, but it is not possible today because the technology today has limitations, and we are still trying to understand what is the best fit for each and every technology. Then saying additive manufacturing means really a lot because it is an extremely fragmented industry. It is fragmented from the technology point of view. It is fragmented from the utilization point of view, and that makes things even more complicated. So I would say that as an industry, what I wish is that we will be able to come together as operators, trying to create the ecosystem that Equinor was presenting as a common ecosystem. What we don't want to happen is that we will have a number of different microsystems instead of one big ecosystem that will be the opposite of standardizing our approach. That will not allow to create a critical mass, and that critical mass is the demand that the operators have to create in order to allow the technology to progress. Technologies are not progressing because they like to do so. Technology are progressing when there is a business case for them to progress. And in order to have the business case, we need the critical mass. What we can do as operators or end users is to define our needs and put the needs together in order to generate a momentum that will allow the actual implementation of an ecosystem and the digitalization of parts and components. In order to do that, we need OEMs to be on board. So the original equipment manufacturers are going to experience a very significant change in the way they are manufacturing today. Additive manufacturing is not going to replace everything. So people, they do not have to be worried about buying printing machines, but definitely is going to change many of the things that they are doing in a better way. In order to do that, again, they have to be on board. There are several points that need to be resolved, like the intellectual property point and the transactional aspects that are extremely important, because at the end of the day, the message that I want to leave on the table is that we need to do it together. This is not something that an end user can do in a vacuum. This is not something that OEMs can do by themselves or additive manufacturers can do by themselves. Is a common effort that we have the responsibility as operators to lead, but everybody has to do his own part. With that being said, I don't have any other point that I have to present today, and we can start the Q&A session.
We have received a few questions from the public, and I'd like to start with the first question. I think that David can reply. Is about the qualification process of powder for additive manufacturing. This is in general, and in particular, the question is if the scrap material like a 316 or duplex will be used. Do you see any particular detail or quality control that we have implemented in the qualification process of the powder?
Yes, so in terms of powder production, regardless in a way of the original source of the powder that goes into the powder production process, the output will have to comply with whatever the specification of that powder is. Now, earlier this year, there was an ISO ASTM standard published. It's ISO ASTM 52907. And that lays out the requirements for powder characterization. So the different tests, different properties that would need to be determined, which tests may be used to determine those properties, and also other aspects in terms of sampling requirements, handling, storage, packaging, etc. So now that ISO ASTM 52907 is published, I would say that that provides some very good guidance on what the quality requirements for the powder are.
Thank you, David. Now we have a question, and the question came from the additive manufacturing oil and gas industry. The idea is to explain to the public how you as end user can involve and ask to the OEM, convince OEM to not consider additive manufacturing as a competitor compared to the conventional manufacturing, but to start to use additive manufacturing as a new opportunities. I think that probably Brede can reply to this question.
Okay, thank you. That's a rather big question. I will try to answer as best I can. Of course, the way I've showed you the picture of this ecosystem and reducing the amount of components we need, it is actually a threat to the OEMs for reducing the volume in the market. So with the existing business model, which is to sell as much physical components to the oil companies as possible, then it's a losing game. But as Valeria showed you, is that you have a lot of new opportunities with additive manufacturing, producing better parts than before. And the other side of it is that we actually now need you to develop digital parts. So we also need to then develop new digital business models which fits to the new additive manufacturing ecosystem. So we have to develop this together. That means I don't have all the answers. Our supply chain specialists, they don't have all the answers. We have to find the answers together on how this can be a thriving ecosystem where everyone can actually see that there's something for them. There should be possible to earn money as an OEM producing digital parts. It should be possible to earn money if you are the just-in-time factory by producing for anyone, for medical, for aerospace, for oil and gas, and so on. So it's a transformation, and usually transformation hurts because you have to start working differently. But I strongly believe that going through this transformation, we will see an increase in activity in Europe locally, because we can now have a much stronger local content than what we've seen before. So my answer is that we have to develop the solutions together. There are still room for all the different kind of companies that we are, but we have to work in new ways.
Thank you very much, Brede. And now we have a question about the API. So API is often considered as a pure American standard. How do you think it will become an international and adopted in worldwide activities from the end user, EPC, and OEM? Carlo, can you reply to us, please?
Yeah, I don't think that API is an American standard. That is proven by the fact that there are API licenses all across the globe. And actually, one of the areas with more API licenses in terms of OEMs is Italy and Europe. So these API licenses are carried and maintained for a reason, because API is the most utilized standard when it comes to products. Okay, you can think about API 6A for wellhead equipment. You can think of API 6D for pipeline and piping system valves. So what I'm saying is that API 20S is going to be an integral part eventually of these product specifications. So it is the only way to get additive manufacturing to be sustainably and viably utilized for API products.
Thank you very much, Carlo. And now we have a question, and I think that we have Andy from Lloyd Register in the background, and I think he can help us. The question is, can you develop or give us example or references on the possibility to reduce energy consumption at additive manufacturing process? Andy, do you have in your experience maybe some case that you can tell us about the energy consumption reduction?
I think it's an interesting question all around additive manufacturing, around the energy consumption. And actually, one of the biggest areas where energy consumption can be reduced is around things like spares and spare parts. If you look in logistics organizations, you look at DHL, UPS, Panalpina, they've all recognized that additive manufacturing is going to have a huge impact on their business. Ones and zeros don't take up a lot of room inside containers, so they're going to have to start moving things around. So if you look at these organizations especially, you can see that they've started to develop an additive manufacturing products. We've got UPS that has a 3D printing plant which has uses their aircraft system to move parts around quickly. DHL is looking very heavily at having 3D printing centers, and Panalpina as well is also looking at this. So I think one of the big things around the energy side of things is that AM is such a disruptor, and it can change the way that people, procure parts, buy parts. you know, it can have a huge effect on the energy. You know, you look at the lightweighting with aircraft, you know, that you save a few pounds on an aircraft, it saves you thousands and thousands of dollars on fuel. You can look at this for automotive, where they're moving to, you know, different hybrid structures. Again, you've got a saving in fuel. So I think additive, in some cases very directly, can have a huge impact on energy consumption, but also indirectly, depending on the processes and the actual products that are being developed at that time.
Thank you very much, Andy. And now another question about API. The question is if NACE is linked to API 20S, and I think that Carlo can reply to us.
No. The answer is no. It's easy, because API and NACE are two separate entities. Okay, so NACE is for corrosion, and API has nothing to do with NACE. Now, API 20S is looking after the qualification of the process, starting from the feedstock to the machine to the first article, and then there is quality controls on manufacturing or production. NACE is something different, something that we recognize it is critical. When I was mentioning strategic initiatives that are happening, I was referring also to the NACE initiative. And I would say stay tuned and look at what is going to happen with the NACE conference next year.
Perfect. Thank you very much, Carlo. And now a question for Brede. How you can involve the valve or component manufacturer for the oil and gas industry in your plans of digital stock?
As I showed you, there are four main roles in our digital inventory model, and the two most important parts for you is the IP owner, actually those who develop new digital parts with better performance, and of course we need a place to produce the parts. And the good news is that in future all the OEMs they can have production facility, but they don't need to. So that means a lot of the smaller OEMs can reduce costs by not investing in production facility. You can focus on designing the digital parts. So in our process now, when we are building the digital inventory, of course we need to build the digital models for all those parts that are going to be in the digital inventory. So in the project, we have already been in dialogue with a few OEMs to start with, but we're going to start a dialogue with more and more OEMs to start developing digital parts. And in some cases, it would be in the first stage, just a copy of the old one. But in the future, we would like to do further development and improve the weight. As Valeria has shown you, that's a very feasible solution to reduce weight, but also you can see that you can maybe increase performance. So I think that's a most important way to go, is start building competence and start preparing for the digital world, the digital inventory, and start designing digital parts. And then we can, as then the next step, to discuss how can we develop the production capacity that we need, and where should those be situated. So we don't have all the answers here. We have to have a dialogue and we have to find the best solutions together.
Thank you, Brede. Now a question for David. He has experience from different sectors, and the question is, which materials that are not standard for additive manufacturing materials yet will be interested in most in the future?
Yes, it very much depends on what industry you're in. So, well, first of all, I would say that it depends. I would always say to anyone looking at adopting AM, first of all, to think, why are they adopting? What is the benefit that you're looking for? So we tend to see three technological benefits. So that are increased complexity, increased customization, or consolidation. So complexity, you tend to get that in aerospace, where they're looking to lightweight components, and you get very weird organic looking structures with much better fly to buy ratios. And the materials for that industry tend to be light material like titanium and aluminium predominantly. In medical, they tend to be driven by the customization side, because you tended to match it to a patient's maybe hip joint or skull or dental implants, whatever it might be. So customization is a big driver for them. And again, lightweighting. So titanium is very popular in medical too. In oil and gas, other than the consolidation aspect, where you would have a multi-stage production or fabrication process that you're trying to build in one go, so avoid those intermediate welds and heat treats, etc. Lightweighting and customization, complexity don't tend to be drivers, which is why in those industries, well, with aerospace and medical, they tend to be driven by powder bed fusion or predominantly powder bed fusion, whereas in oil and gas and energy and marine, they tend to be less interested in those benefits and more interested in the supply chain based benefits. So as we've discussed today, reducing the spares requirement, reducing the lead time. If you're suffering long lead times on forgings, then being able to produce even just a blank by a wire arc process, for example, to massively, hugely cut down your lead time on perhaps a nickel alloy forging. So in oil and gas, we see a lot more nickel alloys, stainless steel, and you can sort of see which are the popular materials based on the ASTM material specs that are coming out. So Ti 6.4 is by far the most popular powder-based alloy, and that's because it's driven by aerospace. But you look at the other ASTM specs that are available, so you've got Ti 6.4, you've got stainless steel 316L, you've got nickel alloys 718 and 625, aluminium alloy, cobalt alloy. I would say the next ones that are likely to come out, possibly maybe even something as simple as a mild steel for tooling. Tooling costs in terms of developing tooling using additive manufacturing processes, or molds by additive manufacturing, such that you can then cast using that mold or die. That seems to be increasing in popularity. So funnily enough, maybe some lower cost materials might be on the way as well. But I would say it sort of links to a previous question, really, in terms of purchasing departments and purchasing power. In order to get that business justification to go to additive, swapping out a cheap component like for like doesn't tend to be a good business justification. So more exotic materials do tend to provide that business justification, and that's why we see probably more of those. I don't know if I've answered the question. I've certainly talked a lot, so apology if I haven't answered the question. Please follow it up in the Q&A.
Thank you very much, David. And now a question for Carlo, as he's the global valve reference for ConocoPhillips. So the question is, one of the key messages is that additive manufacturing can be disruptive if total cost of ownership is considered, including, for example, the carbon footprint reduction. How can this approach be promoted in the purchasing department? And can certification be an enabler for that? Carlo, what do you think?
Now, the certification is necessary, but is not sufficient. Okay, so we are certifying materials not because we like the certifications, but because it's needed from a safety operational point of view. And this has nothing to do with the procurement process. So engineers, and now I'm stepping in my subject matter expert role, is what we require from a technical perspective when we buy certain materials and certain type of equipment. So the certification is going to do that type of assurance. Now, how do we convince? We don't have to convince people. I mean, the technology has to be, again, viable and sustainable. We have more than convincing, we have to explain, even to our own people, why it is advantageous to use, in some instances, additive manufacturing. So Brede was explaining about the huge amount of spare parts that we, all the operators, are stocking. These warehouses, they come with a cost, and that cost is a significant one. So the cost of ownership that is mentioned in this question is exactly that. The cost of acquisition of a piece of equipment is minimal compared to the actual cost of ownership, including all the logistics, transactions, taxes, warehouses, so on and so forth. So by being able to properly quantify these numbers and to show what we can reduce, that is the way that additive manufacturing will potentially have a future. Now, it is, again, not as simple, and by the way, we are always focusing on metallic components. We don't have to forget that we have a lot of non-metallic materials in the oil and gas industry that many times are going together with the metallic component. So we have to focus on sub-assemblies, we have to focus on subsystems, and to see what is the most viable way to produce these systems. And most likely the answer will be that is a combination of additive manufacturing and other traditional manufacturing processes.
Perfect. Thank you very much, Carlo. And now another question, and I will ask Brede to reply, is what about the use of blockchain for intellectual property protection and contractual matters? Thank you, Brede.
Blockchain can be one technology that can be very suitable for all the trust matters that we have in an ecosystem that I described. And in the project that we have started, we are looking into how we can use blockchain to, for instance, make sure that we can lock the model and unlock the model when I, as the end user, order a part. The OEM, the IP owner, needs to unlock the model so that it will be available for the just-in-time factory for production. So there's a lot of trust issues here. Also, when it comes to the payment, the transport, we try to reduce transport, but still there will be some kind of transport. We even look into how we can use drones to transport the parts out to the platforms at sea to reduce lead time further. So all the different players in the ecosystem, they need to be paid. And we know that using blockchain is one method of programming smart contracts so that all these different issues can be handled automatically with trust. But we haven't decided yet whether we should use blockchain or other technologies. There are other options as well, but we really see that blockchain is a very good technology to handle the trust issues.
Thank you very much, Brede. And now we have a question, and I think probably Andy can reply to us, is how to increase the awareness of end users to start with the digital inventory. Andy, in your experience, you talk with many different end users and different industry. What do you think about to promote the use of additive manufacturing and digital inventory?
I think Carlo made a good point before when he was saying that not every part is ready to actually become part of a digital inventory. I think typically of the ones I've looked at, it's probably somewhere between 5 and 7.5% of the inventory is actually probably in a position where you could do something that would be worthwhile with AM from the inventory side. I think it's really a mindset that needs to be created, because what you find is that people do tend to get a little carried away with additive manufacturing and the parts that they're looking at, and they tend to look at what I kind of class as critical parts and quite complex parts. And in fact, additive manufacturing is very suitable for what I refer to as nuisance parts which are very simple but have long lead times, but actually are quite simple. These can be, polymer parts, ceramic parts, whatever they may be. And what I try and do is I try and identify parts which will give a quick win, which is easy demonstrable to the rest of the organization just how good additive manufacturing can be. Now, this could be, a very, very simple polymer part that could be printed in and designed in a few weeks, compared to something which is much more complex and requires a lot more involvement from the point of view of actually designing and printing in metal, doing all the post-processing and testing, etc., which in some cases could be a 12 to 18 month long program. So for me, it's about identifying early wins. It's about identifying simple parts to start with and really getting people comfortable with the idea of what additive can do, rather than just going for this one big showcase piece, which may take a very long time to do and doesn't involve the larger part of the organization.
Thank you very much, Andy. And we have the time for the last question, and I will ask David to reply. It's a little bit technical. What resolution can we have with additive manufacturing? David, can you reply to this?
Well, it depends on the process. So with powder bed, if you're looking for high accuracy, so complex parts, maybe thin walls, powder bed fusion is probably, I'm thinking metal at the moment, then powder bed fusion would be your choice of AM process, but the build times are that much longer. If you are not looking for, and if I think about the minimum walls that I've seen, I've certainly, I mean, 1.5 millimeter wall is quite common, I guess. I have seen 3/4 millimeter wall internal on a heat exchanger, and I'm sure that you can do, I think there was a paper where they were doing even finer walls than that. It might have been, the smallest that I saw was 0.35 mil, but I'd have to double check that against the paper. In other AM processors, so if you go to DD processors, so I guess you've got powder bed fusion at the sort of finest end of the chain, and then moving up to DD, so blown powder or laser metal deposition process, get faster deposition rates, but not quite as high a resolution, and then moving further up to the higher deposition rate AM processes like wire and arc additive manufacturing, for example, or DD arc, I should say, to be not to use trademark names, where the accuracy is far, far less. You would almost certainly have to want to be doing some mechanical post-processing on those parts. So you're not looking at fine structures for those at all. For polymers, I don't really have that information. I don't know if Carlo wants to jump in, then more than welcome. Again, it would depend on whether you're looking at VAT polymerization or powder bed fusion, etc. But Carlo, do you have any info on the polymer?
Basically, the answer is very similar to the one for metals. It depends on the technology. Also for polymers, there are different technologies. I don't have a number because we are actually testing polymers as we speak. We received some samples yesterday with one technology. I would like to make just one small comment on top of what you just said. We don't have to focus on the resolution of the machine, of the printing machine alone. Let's focus on the finished component. And there are different ways to get to the same result. So you can get with a better resolution or even with a lower resolution, because then you can do some heaping to the material, or you have heat treatments and you have final machining. So there are post-processing activities associated with additive manufacturing. I just want to leave the message that additive manufacturing is not necessarily just a finished component coming out of a printer. There are other activities after the printing process is completed.
Can I add one more thing? That's a great point. And one thing I would say to anyone designing for AM, especially if you're starting with a concept that is based on a conventionally produced component and you have an existing drawing that has a surface roughness requirement, for example, before asking for that same surface roughness from your additive manufacturer, question whether you actually need it. What if that surface roughness is actually an artifact of the previous conventional manufacturing process, you may not actually need to achieve that level of surface finish. So before imposing it on an additive manufacturing facility, I would ask the question, do I actually need this very fine surface finish? That I see that quite a lot. So yeah, I just want to make that point.
Thank you, David. And I think we have concluded the Q&A session. And I'd like to thank you, all the speakers, Brede, Carlo, David, and Andy from the backstage. And now I give the stage to Mr. Brancaleone, President of VALVEcampus organization, who hosted this webinar. And I hope it was really interesting. I'm sure we could continue to discuss for at least 2 hours, but maybe in next time. Thank you very much, everybody.
Thanks.
Thanks.
Thank you.
Valeria. Thank you very much, Valeria. Well, we have to thank you particularly because you thank everybody else, but not you. You've done a very good job, not only posing the webinar and by putting us all together. It was very, very interesting. I think that today we are confirming that this Copernican revolution represented by the additive manufacturer is in fact a way of playing with the green and smart manufacturing. We have to put together green and smart because this is something that so far we have not been able to share together. Another aspect I think is very important, where my association, VALVEcampus, is very active, is on the formation and training. And these webinars are just a typical example on how we can introduce the training and formation in a very, very critical period like this pandemic one. And we all hope that as soon as possible, the situation will be better for everybody, and particularly for those countries that are suffering so much at the moment. But I think that information and training goes along hand in hand with the universities and with investments that have to be introduced by companies and by the industry at large worldwide. And I'm sure that what has been said by Carlo, by David, by Reed, and you particularly, will be a very, very important tool. Carlo mentioned also something quite important, very sidewise, the materials which are used for sealing gaskets, whatever is involved with the avoiding fugitive emissions is of course also another aspect where additive manufacturer will definitely have a future. I'm sure that major manufacturers are already looking into that. But I don't want to add anything else. We are just going to 5:30. We wanted to conclude in time. And I would like again to thank our speakers today. Will be on live on YouTube shortly. And whoever registered today as a participant will receive the link to connect, show this to their colleagues and friends. Next year, we will have the Industrial Valve Summit exhibition in Bergamo in May, 26th and 27th of May. And we are working with Carlo and Beria particularly in order to develop a specific workshop on that respect, where we are going to introduce again the additive manufacturing, particularly with the view of large operators and end users. And I'm sure that the experience and feedback that we will get will be very, very important for all of us. Having said that, again, Valeria, thank you very, very much for your effort and your contributions. Thanks to Carlo, thanks to David, thanks to Reed, and I'm sure that we also want to thank Virginia, my secretary, and Veniero, who in the background helped us to overcome technical difficulties that we all face when we try to use. I thank you again very, very much. Valeria, you want to say something else, or Carlo, or David, or Reed?
Yes, Maurizio, I think we can conclude. It was really an honor to speak with the other people, and I hope that the auditor the audience can enjoy and will be more interested to learn about additive manufacturing in the future.
Excellent. Thank you so much to everybody, and I wish you a nice evening or a good day for Carlo that is far away. Particularly to all of us, a better August, and definitely stay safe and try to be as much as possible relaxed. Okay, we'll be in touch with you all, and we will shortly keep you informed of any short activities that we are planning. Thank you again to everybody. Bye-bye.
Thank you.
Thank you. Bye-bye.
Bye. Bye.